All right, stat students, we are going into chapter 5, and I have contacted you by this time about our processes and what they'll look like as we are doing things online. Chapter 5 is probability, and a lot of this is going to be familiar to you from basic probabilities that you've done in Algebra 1, and we're going to go through a lot of the language, though, that may be new, but keep in mind that all of this is based on the fact of, the probability of a simple event is the number of favorable outcomes divided by the total number of outcomes. So that's kind of what we're working through in this chapter, or this particular section of this chapter is just going to be dealing with that. So let's roll on a little bit. 5.1 is going to be probability rules. And we can look at the individual objectives. There's a lot of them here of applying the rules of probabilities. We're going to look at computing and interpreting probabilities using the empirical method. And we're going to be looking at computing and interpreting probabilities using the classical method. And again, those two things are not really new for you. The language may be. We'll want to use simulation to obtain data based on probabilities. And we'll talk about those simulations without actually doing them. And then we want to recognize and interpret subjective probabilities. So that's the 5 objectives that we'll look at in this first section of Chapter 1. So let's define what probability is to begin with. Probability is a measure of the likelihood of a random phenomenon or chance behavior. So probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. So an example of this, it sounds like a really complicated thing, but we could write, what is the probability of rolling or heads when flipping a fair coin. So the probability of heads is 1 out of 2 because there's 1 head and 2 complete. So that's a probability of the measure of a likelihood of a random phenomenon. It describes the long-term proportion. And what this means is the long-term proportion. It is quite possible that you could actually flip a coin 6 times and get heads 6 times in a row. But it would be almost completely unlikely that you would flip a coin 60 times and not get something that is particularly close to 1/2. And certainly if we flip the coin 6,000, so the more times we do it, the closer the actual probability is going to be to the theoretical probability. So that's what the long-term proportion, with short-term uncertainty means. So the probabilities of that event, or likelihood of that event, is 1/2. So probability deals with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. And so the long-term proportion in which certain outcomes is observed is the probability of that outcome. So, back in Algebra 1, when you guys had Algebra 1, this long-term part is what we call the theoretical probability. It takes a little bit different name in this particular text. We'll discuss that a little bit later. And then this short-term things that we observe are experimental. So experimental probability and theoretical probabilities get really close when the number of experiments gets really high. So that's kind of some things that we'll talk about here with the law of large numbers. Says as the number of repetitions of probability increases, the proportion with which a certain outcome is observed gets closer to the actual probability of the outcome. So when we're looking at experimental outcome, right, is the probability of repetitions of the experiment increase, then the experimental probability is going to get closer to the theoretical probability. So the more times we flip that coin, the more likely the outcomes are going to get to 1/2 and 1/2, 1/2 heads and 1/2 tails. So it gets closer and closer and closer. And we've already talked about the coin flipping, so that's where that comes from. So in probability and experiment, is any process that can be repeated in which the results are uncertain. So anytime we flip a coin, there is absolutely no guarantee of what's going to happen next. So it's complete uncertainty, even though there's a small number of possible outcomes. But we could talk about rolling a die. The same thing happens. There's only a limited number of outcomes, but we have no way of predicting exactly what that next roll is going to be. So the outcome is uncertain. The sample space of a probability, the sample space, capital S is the variable assigned to this in statistics, is the collection of all possible outcomes. So if we talk about this for just a moment, we talk about the sample space of, let me look at where I am here. The sample space is for flipping a coin, for example. If we're talking about flipping a coin, then the sample space is the set of the possible outcomes. Well, there's only two possible outcomes for flipping a coin, so heads or tails. Okay, but if we talked about maybe the sample space for rolling a die, okay, for rolling a die, then the sample space would be the possible outcomes. 1, 2, 3, 4, 5, 6. It's the set of all possible outcomes of an experiment. Okay, so we talk about sample space. That's everything that could possibly happen. All right, let's talk about the next definition, an event. An event is a collection of outcomes from a probability experiment. So an event may consist of one outcome or more than one outcome. Now let me tell you what that's talking about there. We could get into an event could have more than one outcome. We're going to look at in just a minute, the probability of having a boy, one boy in a 2-child family. So there's more than one possible outcome that could take place there. So the event is a collection of outcomes. What's the probability of having a boy and then a girl? Or what's the probability of having a girl and then a boy? And so we can talk about multiple outcomes being an event. Another example of that could be what's the probability of rolling a 2 on a fair die and then rolling a 6. So that's the event is rolling a 2 and then rolling a 6. So that's the what it means by more than one outcome. Okay, it says we'll denote simple events with one outcome, sometimes as simple events, E sub I, and in general events are denoted using capital letters such as E. All right, so that's like where we had earlier, I said the probability of H, right? Capital H is heads, and the P is the probability of heads. So that's kind of the notation. Not a whole lot of complicated stuff there, just giving us, again, language that we'll use to read problems. So here's our first example from this lesson. It says, consider the probability experiment of having 2 children. Okay, so a family with 2 children. Identify the outcomes of the probability experience. So what we're talking about, the possible outcomes, and it's also the letter A kind of rolls into letter B. So the number of outcomes we have is going to be, the first thing we will have is we could have a boy and then a girl, right? We could have, so that's one outcome. Let me kind of put these so they're separated. Another outcome could be boy and then a second boy. There's another outcome. And then we could have the possibility of having a girl first and then a boy. Or we could have the outcome of a girl and then a girl, 2 girls. So that's the 4 outcomes of the probability. So the sample space then becomes the set of these things. So letter B, the sample space is just boy, girl, boy, boy, girl, girl. All right, so then C says define the event of having one boy. Well, the event of having one boy means we could either have a boy-girl, right? So this is an event that has one boy, or we could have girl-boy, and that's another event that has exactly one boy. And I really, really wish in mathematics that this says exactly one boy, right? If it said exactly one boy, and that's what it's talking about, that would be a little bit more specific. Because technically, if you have two boys, you have one. So in mathematics, we like to be a little bit more specific. Exactly one boy is really what this is talking about. So if we move into applying the rules of probability, we could talk about this, in advance a little bit. I think we can do this because you guys know enough rules of simple probability. So if we go back to, let me see if I can go back to what I did last. Where is that? It's not going to be available to me. But we had the list of outcomes. We had boy, girl, boy, boy. We had girl, boy, and then we have girl, girl. So if we talked about the probability of having exactly one boy, right? Probability of one boy. That is in a two-child family, of course, two children. That would be two choices out of four, which would simplify to 1/2, okay? And we could go and look at the probability of two boys in a two-child family would be 1 out of 4, and so on and so forth. So once you define the sample space, and then you can look at the favorable outcomes and the possible outcomes. So we're finally getting into a little bit more specific rules of probability. And again, this is not new. The probability, this first rule says that all probabilities, the probability of any event, has to be between 0 and 1. So you can't have a negative probability, and you can't have something with more than a 1 likelihood of happening, right? So it's impossible for something to be 110% likely to happen. It's either going to happen. If it's absolutely guaranteed to happen, the probability is 1. If there's no possibility of it happening, it's 0. But in reality, most probabilities take place somewhere in between those values. Okay, and then the second rule of probability, the sum of the probabilities of all outcomes must equal 1. That is, if we have a sample of space of all these possible events, right? All these are possible events in our sample space, then the probabilities of each event happening have to add up to be 1. All right, so that's to the two basic rules of probability. And these probabilities were true of our frequency distributions that we've already done in our samples up to this point. So that's a couple rules we'll look at. A probability model lists all the possible outcomes of a probability experiment and each outcome's probability. The probability model must satisfy rules 1 and rules 2 of what's going on there. I think we may have an example of that next, and we do. Okay, so here's a probability model. In a bag of peanut M&M milk chocolate candies. Yum, right? The colors of the candy are brown, yellow, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. The table shows each color and the probability of drawing that color. Verify that it is a probability model, okay? In order for it to be a probability model, all probabilities have to be between 0 and 1, right? And that's true. All these probabilities are less than 1, less than or equal to 1, greater than or equal to 0. So we're good there. Rule number 2 is that the sum, oh boy, let's do this using our sigma notation. The sum of the probability of each event has to equal 1. And if we add those together over here, if we just did a running kind of a frequency cumulative thing. This is 27, 39, 39 and 23 is 62, 62 and 23 is 85, and 85 and 0.15 is 0.10. So all of the probabilities add up to this. So this, we can verify that it is a probability model because it meets these two characteristics of what a probability model is. All right. Now, all probabilities are and they do add up to 1. So we're looking at. All right. If an event is impossible, the probability of the event is 0. If an event is certainty, the probability of the event is 1. Okay. And an unusual event is an event that has a low probability of occurring. Now, low probability is relative, right? It's a low probability is relative. For example, the current thing that we're dealing with here with the coronavirus or COVID-19, the probability of dying from this virus is low, right? There's a low probability that is going to occur. So it would be unusual and unlikely for us to know anyone that dies from this virus just based on its mortality rate and its transmission rate. So it would be considered an unusual event. Low probability of occurring. And we'll talk a little bit more about specifics about where that cutoff is a little bit later. So objective 2 is to compute and interpret probabilities using the empirical method. Now, if you talk about empirical method, empirical, right, the word empirical is generally something that you can taste, feel, touch. The empirical method is it's replacing experiment. Right? It's the experimental method because we're actually taking a die in our hand and rolling it 10 times. Okay, so it's observed, right? Something that we see, it's experimental, it's observed. So this goes back to our experimental probability in Algebra 1. So the experimental probability is not going to always equal the theoretical or what they call classical probability in this particular book. So the probability of an event is the number of times the event is observed divided by the number of repetitions of the experiment. Okay, so it's favorable over possible, but we're dealing with experimental data rather than theoretical data. So here's an example. Pass the Pigs is a Milton Bradley game in which pigs are used as dice. Points are earned based on the way the pig lands. There are 6 possible outcomes when one pig is tossed. A class of 52 students rolled pigs 3,939 times. The number of times each outcome occurred is recording in the table at right. Okay, so this is definitely not a simple probability event because the outcomes are not equally likely over here. So we can talk about the probabilities of these things. Now, this is an experiment, right? This is an experiment because points are earned as 6 possible outcomes. The number of times this class did 3,939 times. We get the experimental outcomes. Okay, so that's recorded it right. So we could take each of these outcomes, and we could talk about the probability. So use the results to build a probability model for the way the pig lands. Estimate the probability that a thrown pig lands on a side with the dot. Okay, the probability of the side with a dot for letter B there, the probability of the side with a dot is equal to 1,294 out of the total number of rolls, which if we look back on the previous slide was 3,939. And using the calculator, we could get a decimal approximation for that. Let's use 3 decimal places, but the probability is that. So, you could estimate it 12 out of 39. There's really 13 out of 39. This is about 1/3, so that's kind of what you'll see when you do those probabilities. And then it says, would it be unusual to throw a leaning jowler? Now, leaning jowler here is 32 times out of 3,939. Now, relative to the other outcomes, the next closest one, the snouter, is nearly 4 times more likely to happen than the leaning jowler. So the answer is yes. Particularly, relatively speaking, this is less than 0.1, right? 32 out of 3,200 would be 0.01. So this is less than 0.01. It has less than a 1% chance, which would certainly classify it as being unusual. All right, really, we could probably at this point, for this early section, let's say that if it's less than 5%, or considerably less than the probability of the other outcomes, then it is unusual. All right, so the part A says to use the result to build the probability model for the way the pig lands. And the way you would do this, the probability for the side with the dot was, 13? Let me go ahead and just do this so you can see it. Probability of side with no dot was 1344 out of 3939, which is 0.341. And then the probability of side with a dot, which we did just a moment ago, 0.329, and then so on and so forth. Now, if we took the time, a probability model here, these values, and we got 3 decimal places here, which is really probably going to ensure that those things add up to being 1, or, if we get 0.999, something like that, then we're probably in safety land for saying that this is a probability model. But if we extended it to, we could always extend it to further decimal places to make sure that it add up to be exactly 1. Okay, so constructing a probability model, I want to note at this point, and we may have passed over it in one of our previous notes. Maybe we did, or maybe we didn't. We did not, or maybe it's coming in just a minute. The probability model is the same as relative frequency models that we've looked at up to this point. And we've been talking about probability and relative frequency and how they relate to each other along the way through chapters 1 through 3. All right, so objective number 3. Compute and interpret probabilities using the classical method. Okay, and the classical method, this is our good old theoretical probabilities, right? We're not using experimental data. We're using theoretical data. The classical method is theoretical probability, is the term that you are doing this. The classical method of computing probabilities requires equally likely outcomes. So that pig in a blanket or whatever game we just looked at, obviously that experiment shows that those probabilities are not going to be equally likely outcomes. But an example of something that has a probability of equally likely outcome is rolling a die. The probability of rolling each number is equivalent if the die is fair. And we always assume that it is. Okay, so equally likely outcomes is what that means. An experiment is said to have equally likely outcome when each simple event has the same probability of occurring. Okay, so computing probabilities using the classical method or the theoretical method is if an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is m, then the probability of E is m out of n, or m over n. It's the number of ways E can occur divided by the number of possible outcomes. So it's favorable. Again, if we go back to our Algebra 1 definition, it's favorable over possible. All right, so favorable over possible. The number of favorable outcomes divided by the total number of possible outcomes. All right. Probability, so if S is a sample space of this experiment, again, this is another way of saying the same thing. The probability of E occurring is the number of times, okay, let's go through this. The probability of E occurring is the number of times that E occurs divided by the total number of things in the sample space. Again, that's favorable outcomes over possible outcomes. So favorable over possible. This is basic, simple probability. And this example shows that. So it's talking about a fun-sized bag of M&Ms contains 9 brown candies, 6 yellow candies, 7 red candies, 4 orange candies, 2 blue candies, and 2 green candies. Suppose that a candy is randomly selected. What is the probability that the candy is yellow? Okay, so the probability that the candy is yellow is equal to the number of yellow candies, 6, divided by the total number of candies, which is 6 and 7 is 13, 17, 19, 21. 6 out of 21 simplifies to be 2 out of 7, and you could assign a decimal value to that. But 2 out of 7 is between 0 and 1, so it is an appropriate way of expressing the probability. The probability that the candy is blue is 2 out of... Oh, man, hold on. I need to back up. I made a mistake. I left out the 9 brown M&Ms up there. 6 out of 30. 1/5 or 0.2 probability there. The probability that it is blue is 2 out of 30, which is 1 out of 15 or 1/15. Comment on the likelihood of the candy being yellow versus the candy being blue. Okay, since there's 6 yellows and 2 blues, we could say that the probability of yellow is 3 times more likely. It's 3 times more likely to occur. Okay? Probability of yellow is 3 times more likely than the probability of blue. So that's what it means. Comment on the likelihood, so we can compare those two things. And incidentally, this goes back to the level of measurement that we're talking about here. This is the ratio level of measurement, because these statistical values are comparable by multiplication and division. So that's simple probability that we're talking about here. So when notation gets complicated, like you see notation that looks like this, don't lose sight of the fact that we're just still dealing with simple probabilities, and the notation gets more complicated before it gets more simple. All right, 4, and we're not going to actually do these simulations, but we'll talk about these simulations. Use a probability applet to simulate throwing a 6-sided die 100 times. And it says approximate the probability of rolling a 4. Now, approximate the probability, the reason that it uses this language is because we are doing an experiment, okay? And an experiment is going to approximate the probability. And if we go back to the other thing that we mentioned earlier, the law of large numbers, if we repeat the exercise 1,000 times, then the experimental outcome or experimental probabilities are going to really get closer and closer to the theoretical probabilities or the classical probabilities. So we know that the classical probability of rolling a 4 is 1 time out of 6. That's the classical probability of a 4. Okay? Now, if we rolled a die, 6-sided die, 100 times, that means we could expect to get 1/6 of 100 rolls to be 4s. Okay, so whatever 100 divided by 6, we would expect to have that many 4s. And if we repeated the exercise 1,000 times, then that number is going to be statistically closer to exactly 1/6 than if we only rolled it 100 times. So that is, and then there's applets and things that you can use to simulate this. But the theoretical outcome, the theoretical probability of rolling a 4 is 1 out of 6. If we roll it 100 times and 1,000 times, the difference is that we should expect that the 1,000, this experiment is going to have a probability that is really closer to 1/6 than the if we just do the experiment 100 times. And so that's kind of where you get that. All right, so this last objective in this section is really just about recognizing what subjective probability is. Now, something that is subjective means it's related to a person's opinion, right? An objective test is the answers A, B, C, or D. Subjective test would allow the teacher to decide the number of points that a question has earned or a comment is earned. So there's some subjectivity to it rather than being completely objective. So subjective probability is a probability obtained based on personal judgment or an opinion. For example, an economist predicting that there's a 20% chance of recession next year would be a subjective probability because it's an economist's prediction or their opinion. Okay, in his fall 1998 article in Chance magazine, Hal Stern investigated the probabilities that a particular horse will win a race. He reports that these probabilities are based on the amount of money bet on each horse. When a probability is given that the particular horse will win a race, is this empirical? Okay, is it actually experimental is what that means? Do we run an experiment to do this? Is it classical? In other words, we can find what the theoretical probability is of the horse winning, or is it subjective? Okay, and because this particular writer's investigated the probability and he based it on the amount of money bet on each horse, right? And the amount of money bet on each horse is based on people's opinions about whether that horse is going to win. And because it's the opinion of people that determines the probability, then we are going to say that this is completely 100% a subjective, okay, probability, because it's based on the people's opinions or feelings about whether the horse will win a particular race. Okay, that's it for this section. Your homework is this. Now, this is a lot of work, and you will be able to, on the message board, if you have any questions or comments about this, you'll be able to do this. And I'll send you emails, and we'll determine who has the ability to email a screenshot of the homework to just confirm that it's done, and we can go from there. I'm also working on scanning in the answers, so the answers to the homework problems will be available to you, so you can check your homework and know whether you need to ask questions or not. But ask questions on the message board in Power School Learning, and you can also upload or email me a picture of this homework from 5.1, and we'll go from there. Again, email me or comment on the message board with questions, and have a great day.